I appreciate Professor Sang to invite this Discrete Math seminar. So, okay. So this is the content. So I heard that only a few people knows about what is model theory. So I think I have to briefly show you what is the model theory, and then some interesting facts about the graph and model, and then the Mekler's construction. So for today's seminar, I will focus on the things that is related to graphs rather than some theories and lemmas, which requires a deep understanding of model theory. So, okay, let's start. So in model theory is model theory is actually in mathematical logic. So first thing you need to know is the definition of language. A language L is a set of constants, function symbols, and relation symbols. Because some English sentences may cause some paradoxes like Russell's paradox or Berry's paradox, we use only formalized language. For example, here we have a language of group. The language of group consists of constants E and binary relation dot. So, for example, if you make this kind of sentence for x times E is equal to E times x, and this equals x, then this is nothing but the English sentence that E is a multiplicative identity. And then second one, for x, there exists y such that x times y is E. This means that, yes, for any element x, there is a multiplicative inverse. So that's it. So this kind of English sentences can be formalized to this kind of form by only using the language and some for there exist, etc. And look at the example number 2, the language of a graph. Here we only use R, which is a binary relation. So let's see, for x and for y, R, x, y. This means that x and y have something relation, which is definitely an H relation. So this is the language. So you can easily understand what we want to show. And because we defined a language, the next thing is a structure. So please look at the definition. Let L be a language. An L structure is a tuple M, which consists of A, C, F, and R, where A is a non-empty set. We will call this A as the universe of M. And 1 to 3, we have constant, function, and relation symbol, which was already in the language L. So, for example, please look at this example that I drawn in Blackboard. For example, somehow you want to work on graph language with some graph structure. For example, you have A, B, C, where A and B is connected and B and C is connected. Then the universe of this structure, for example, let's say this structure is M, then the universe is the collection of nodes. So A and B and C. And to explain how this structure looks like, you have to say about the relation R. So this is the one. So because we are not working on the directed graph, we have to say that this R contains A comma B and B comma A. Actually, there are two directions, but okay, let's skip this one. And then B comma C, C comma B, and that's it. Because this relation does not contain something like A comma C, we can easily know that there is no actual relation between A and C. So this is the basic notion about the structure. So, okay, you have some structure, and to explain how this structure looks like, you have to use some specific language, and then this kind of things. And then there is a next definition. Okay, before that, please look at the first example. For x and for y are xy. This is nothing but a sentence, but in this structure, this sentence is false because A and C are not related. So this is false, and definitely we have an interest in some set of some collection of sentences which is true in some specific structure, right? So here we have this definition. THM, the full theory of M, is the set of our sentences phi such that phi is true in M. Yes. So easily say you collected all the true sentences in some structure, then that is THM. Where this kind of simple structure, we can easily see how the THM looks like, but this is the simple cases, and for other not so simple ones, the THM is very hard to see. Okay. By the way, do you have any questions so far? No?
Can you give me an example of a universe with non-constant element?
I'm sorry, universe with?
An example of a universe with non-constant element.
Non-constant?
What's the meaning of constant?
Oh, okay. Constant is nothing but, okay, for showing the, to explain to answer your question, it's easy to construct a group example. For example, so, okay, this one is universe. And universe, in universe G, you want to talk about some identity, then this x is variable, but this specific one is constant. So in this structure, well-known structure, you can use some constants as follows. Do you understand? Okay, thank you. Okay, so the basic idea is you think about some structure and you want to explain this by using some specific languages to find out what is true or what is false. And now I have to explain about this definition about the interpretability. We say that on L0 structure N is interpretable in an L structure M if there is a definable X, a definable equivalence relation E, and for each symbol blah 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 blah. And okay, I admit that this definition contains too many terms that I didn't explain to you, but if you see the example, then you will know what the interpretability is. It's actually very easy concept, and you actually learned about it. Okay, so please see this example. For interpretability, I make this example Z and Q. So the first one is this one, and second one is this one. So as I said earlier, this one is the universe, and they are languages. So this M has the universe as the set of integers, and N, and has the universe as the set of rational numbers. And you know the addition and multiplication in both integer and rational numbers. So let's go deeper and deeper. So if you learned set theory, you will probably shown that how to construct rational numbers in integer numbers. That is nothing but this kind of form. So this says about the construction on integer numbers to make rational numbers. Okay. Rational numbers is constructed as, for example, a half, and so on. Okay, so you want to use this kind of notation, but sadly there are no fraction term in our language, so we have to use another way to make the rational numbers. So the technique is this one. Interpret this as a tuples, but here you don't want to make 0 in the denominator, so you have to assume that we are not gonna use something like this one, 3, 0. This means that if we use the variable x0 and x1, we have to claim that this x1 is not equal to 0. But unfortunately, this constant 0 is also not in our language, so we have to use another way to express this 0. That is, as we know, this 0 is additional identity. So you use that for y, x1 plus y is y, and then we wanted to say it is not 0, so make a negation sign. So that's it. So this one just says that x1 is not 0 by using only plus and times language, addition and multiplication language. Okay? This is the first step, and the second step is equivalence relation. As you know, 9/6 is equal to 3 over 2, and this is equal to 12 over 8, and so on. So you have to define some equivalence relation on these tuples. That is, yes, easy. They're same when as I said earlier, we cannot use this kind of term, so just use this multiplication to say that we are working on this kind of rules. And then plus and times. You can see that, for example, times means that nothing but the this one is exactly the same as this one. The difference is that this sentence only uses the time relation. I write down the dot, but it's the same. Okay, so that's it. We defined the domain, that is x1 is not 0, and we defined the equivalence relation to say about this equivalency, and then we define the plus, we define the times. So the result is that we can define the structure Q inside the structure Z. So that's the interpretation. For interpretation, we use gamma notation. So gamma and this equivalency and plus times. And done. Okay, any question on this interpretation and examples? Okay, so this is the most easiest interpretation example, and I will gonna show you much harder ones next time. So now let's go to the section of graph interpretation theory. The first example just talk about the interpretation of Q in Z, but this theorem tells us that any structure can be interpreted in some graph theory and vice versa. So, okay, let's see. Let L be a count of first order language and K be a language of graph theory. Then, for any structure B of L, there is a graph model A of K such that B is interpretable in A. So, our first example was that G, or precisely G times, there is a structure Q inside this one, and this theorem tells about that if you have a arbitrary structure M, then you can find some graph and such that the structure lie inside the graph N, which means that if we want to investigate this M, you can just see the graph N, whatever this M actually is. For example, you can interpret some group in the graph, you can interpret some field in the graph, and so on. So let's see how this is possible. I just write down the sketch of a proof. I think this would be the most interesting theorem for the graph theorist, maybe.
Could you return to the theorem for a second?
Oh, you want this one?
So graph model is finite or possibly infinite graphs?
Possibly infinite, because, for example, your target M may be infinite, then this graph N should be infinite too. Maybe you can do this in some finite model, but generally it's impossible. So this is the sketch. First, we define the tag. We say an element A is n tagged in a graph if it contains the first configuration, which means this one. So you have A, then tag means this one. Yes. So n tag means that this cycle has n nodes. So that's it. By tagging this kind of things, you can identify the node A by using some languages and some sentences. Okay, that's it. And then build up A as follows. So first, we have empty set, then add vertices A1, A2 to A kappa, where kappa is B. For example, you have A1, A2, and A3. So the universe is A1, A2, A3. Then from this one, from 0, you add these 3 nodes. Then second, for each vertices AI, make it 5 tagged. So here, you make tag here. And then third, for each KRE relation, R in K, for each AI to AI1 to AI K in R, make the second configuration where D is K plus 6 tagged. So look at this configuration. Here we have a relation R, and we want to make a meaningful relation here in graph. So look at this one, A and B. Oh, I see this one. This should be A1, 2, A2, 1, and so on. Anyway, you want to tell that this is a valid relation, then this is the first one, so add a node, second one, add 2 nodes, then you have something D, and then tag. Again, you have a relation, so 1, 2, tag. Because we are working on the binary relation, the graph looks very simple. But if we are working on, for example, ternary relation, something on, then you have to make a configuration, single node, double node, triple node D and take. Because the node between A and D, the number of nodes between A and D are different, we can easily see that ABC has a relation with the order ABC, not CAB. So that's the basic idea. And also, look at this tag number, K plus 6. Because of this 6, only the five tags happens in here. So you can easily see that the nodes which actually comes from the universe is this one and this one, this one. You can easily determine from our whole graph. So that's it. You make some nodes, you make some tags, you make some another tags to determine the R. And okay, the fourth one is not easy actually. Do the similar construction for function and constant symbols in K. That means you have to make a similar construction we worked in relation. It may look very difficult, but the functions is actually nothing but a relation. Why? Because, for example, you have C comma D is E, then this means a relation. So I need to use suffix C comma D comma E. And if you have some kind of constant C, then you make a characteristic relation such that only C is true in here and nothing else is false. So any functions, any constants can be considered as a relation, and any relation can be coded in this kind of form, and then you constructed the graph, which contains the whole data from our original structure. So this is the graph interpretation theory. You can interpret. You can make a code. You can make a code of the form of the graph, of the graphical form from any structure, anything. So we learned that, okay, we have any structure, and by coding this kind of thing, you have a graph. That means if we have some specific example of some structure, then by doing this kind of thing, you can have a graph example, right? So that's it. And then Mekler did something more strange things. That is, from this graph, you make a group. So from now on, I will talk about the Mekler's construction, which tells us about a way of constructing group from graph. For this one, first to look at this definition. A graph A, which has at least two vertices, is called nice. Why did he choose the word nice? I don't know, but maybe he was very exciting about his development. Anyway, okay, there is two conditions. The first one is that for any two distinct vertices A and B, there is some vertex C which is connected to A but not connected to B. Here, okay, choose this one and this one. Then this star is connected to A1 but not connected to D. Look at the second condition. There are no triangles nor squares. This is why we choose the tag as the pentagonal shape. No triangle, no squares. So what is interesting in this kind of nice graph? That is, by working on the nice graph, we can get some theorem of Mekler's. But before that, let's look at the definition. Suppose you have a nice graph. For example, this one is very good example of nice graph. From this nice graph, we generate GA, a Mekler group of A, such that GA is a free group generated by the vertices of A. That means the GA is nothing but a word group. For example, the ingredients are the nodes. So A1, A1, A2, D1, D1, A1, A2, A3. This kind of words are inside this Mekler group, and definitely the binary function is nothing but the concatenation of two distinct elements. I mean words or strings. Anyway, so you generated this GA, and then you multiply some special rules. The first rule is that for X, Y, and Z, the commutator of X, Y, and then make another commutator with Z, then that one is 1. If you learn the algebra, you will remember that X times Y is X inverse Y inverse XY. And look at the C. For every element X, X to the P is equal to 1. That means if you make a word with the length P, then this is equal to identity. So, well, this one can be interpreted as xp minus 1, yp minus 1, xy.
Sorry, I have a question.
Mm-hmm.
Where do the edges of the graph come into play, into account?
I'm sorry, the edges of the...
Right. The definition is only concerned with the vertices of the graph, and
Yes.
the edges don't seem to matter. So,
Mm-hmm.
makes sense?
Yes, you are right. Yes, I forgot something to write down on. Okay, I'm sorry to not to write down the important ones from edge relation. I mean, what should I say? You have a graph, and another special rule is that if X and Y are generators, and in the graph, if they were connected, then they commute. Or in other words, the commutator is 1. I'm sorry to omit this one.
Thank you.
Okay, so the graph contains some data from the graph. That is, it has a generator as a node, and this commutating rule contains some data of the active relation from the graph, and B says about some nilpotency, and C talks about some periodicity of this word group. And then, with some very hard work, Mekler find out that if you have a nice graph A, then A is interpretable in the graph. Very interesting. So the stream is as follows. You have a structure. From here, you have a graph. And from graph, by Mekler's construction, you have a group. We have a group example. There are some hard problems about group theories, whether there is some special, or what should I say, some counterexample graphs exist or not. That's the question. And by Mekler's construction, we somehow get some ideas to find out the group examples.
So is every graph you construct from structure nice?
Yes, the nice is important.
And you have a first arrow, right? So you get some graph that constructions. So that.
Oh, you want to ask me that this may have some possibility to fail the property of nice. Then it is this may not nice. Is it your question? Well, actually the construction always makes a nice graph. Actually, the first proof of this Lavrov's theorem, the tag was actually triangle. The tag was actually triangle, but Mekler somehow find out that triangle in the graph makes not a good result. So Mekler made this as a pentagon, and as you see, there are no such, for example, dead end like here. If we have a dead end in the graph, then the condition A may fail by choosing this one and this one. But here, you don't have any dead ends, so the condition A holds, and also no triangle, no square. There is a very good example. For example, you have a relation which is which just tells us the equality. Then equality means that A1, A1 is possible, but here, because we have one node, and here we have two nodes, this one cannot be triangle nor square. So this nice graph, so this construction always makes a nice graph. And then the interpretability rules. So, okay. So the structure lie inside this kind of things, graphs and Mekler groups. So I will show you what I've found out. The definition contains a lot of difficult things. Let T be a complete theory and blah 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 and blah 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 and blah 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 blah. Okay. Do not focus on the definition, but please look at the examples that I'm interested in. Q and order relation. You learned about the structure, right? So this Q is the universe, and this order relation is the predicate we want to talk about. So you have Q. That order relation is linear. You can work on this kind of diagram, and by choosing the sentence phi with variables x, y1 and y2 by choosing this one, a very simple formula, right? You can do some very interesting things. I will write down the phi in the upper side. If you plug 0 and 1 to here y1 and y2, you have a simple open interval from 0 to 1. And then by choosing another one, 0 and a half, we have another open interval which is in here, right? And then make another thing. Erase this one. Another open interval and the last open interval. So the open interval now getting chopped out to make some infinite tree. This shows that this simple formula can make this kind of infinite tree structure. But here structure is not as same as the previous one, by the way. So as a model theorist and as a model, many model theorists are interested in this kind of infinite tree because, for example, if you have Z, this kind of infinite tree cannot happen in here. So we believe that this kind of property is important to tells us between this structure Z and this structure Q. Now, let's look at here. So we know that this Q with order relation have this kind of infinite tree. So here we have infinite tree here, and then this, even though this structure actually not a graph, rather a ordered linear things, you can construct a graph, actually an infinite graph, which has this kind of examples, and then Mekler group, you have these things too. So this kind of thing is called the tree property of the first kind. If some theory have this kind of TP1 formula, we say this T is TP1. If it does not have, we say this theory is NTP1. And then many model theorists find out that this kind of property works on both sides. That is, theorem C is stable if and only if theorem GC is stable, which was found by Mekler himself. So that this gives us a stable example of group from stable structure, and then simple, and then NIP, and then NTP2. So from their works, I found out that the property NTP1 also holds to this vice versa property. That is, theorem C is NTP1 if and only if theorem GC is NTP1. Okay, so that's it. For final word, if you are interested in this kind of structure, please look at this book, Wilfried Hoch's book, Model Theory. You can find out how this can be done. And then so on. Okay, so thank you.